Hello, this is Mrs. Schaefer going through some highlights for lesson 4.06 and 4.07. As you go through this lesson material, you'll want to watch this video and also the videos that are in the course to help you review and make sure you've got everything that you need to understand the material. If you're a late start student, please remember to go through your welcome email to determine what assignments you need to focus on to help you as you complete and catch up the physical science course. If you need any help, please be sure to ask for that help. So this is covering 2 lessons. Think about what you already know. Rate yourself. Where are you? Are you a beginner? Are you starting to get some things about these topics of radioactivity and radioactive decay? Are you proficient, meaning that you could pass the test right now on that, or I've got it, you could explain this to someone else. So rate yourself now, and then at the end of the lesson material, go back in and rate yourself. Have you moved and made progress? Even if you have to go through this material more than once, that's a-okay. You're learning and getting what you need to help you so that you can master the material. Anytime that you are feeling confused or stuck, please come back to this chart and use it as a checkoff. Check off each of the defines. Make sure you can define each of the terms we're introducing, along with then can you describe it? Not just give me the definition, but can you look at it in a different way and explain how it's used or how it happens in uh, in in the physical world. Then you can look up to the next step. The next progress level is being able to calculate half-life and explain to someone how to do that, or to evaluate and predict. So each one of these gets a little bit harder. And if you get the easy things, then it's easier to move up to the more challenging things. So use this as a checklist to help you determine if you've got everything that you need to show mastery for the lesson material. We will be looking at the review sheet questions 4 and 5 in this. Remember that in the lesson material there will be an active link here, but you can also find it in the course. Either way, to help us start with radio activity, we're going to go back and talk about those isotopes again. What's an isotope? Look at this picture and explain to me how they're the same and the different. Pause the video until you're ready to move on. All right, so as you go through and review, it will help explain the idea of what we're going to cover for radioactivity. So sometimes nucleuses are unstable and they want to balance, but they don't. So an unstable atom will try to decay. It will try to reach balance. Um, an atom is in balance if it has the same number of neutrons as protons. And we talked about the idea of isotopes, and that is where we get this idea that we're going to discuss today. So tell me, what do you know about radioactivity? I'm sure you've heard it before, at least the word. So think about what you already know. Then go in and compare it with the video. This is an introductory video on radioactivity. And then list out in your notes what you learned. It's really important to take that time to think, this is what I know and this is what's new, because it helps your brain store the new information and add to what you already know. So particles want to escape from an atom when they're unstable. That's called radioactive decay. It wants to become more stable. And these protons and neutrons are attracted to each other. But remember from your magnets that positive and a positive repel each other, a negative and a negative repel each other. It's the same thing. Protons have a positive charge. So when they get too close to another proton, they're going to repel each other, causing the electromagnetic forces to come into play. Well, they're squashed together in the nucleus, and that has to be balanced. That force has to be balanced. And that can happen a lot in the elements is that there is some repelling of the different protons or pieces of the nucleus, especially as the elements become larger. Larger things are more unstable than smaller things. So here's a picture of the electromagnetic forces that are in the nucleus. So the protons want to try to get away from each other. The neutrons are there to help balance out that force. So there's also a strong nuclear force. So in the nucleus, you're looking at electromagnetic forces and nuclear forces. Just like in that magnet with the positive charge, it's going to repel each other. Nucleus have no charge. So they kind of cushion and balance and separate those proteins out. So there's nuclear forces and electromagnetic forces. And those are both opposite forces. You can see the arrow here is pointing away, and then the arrow on the nuclear forces is pulling them together. Whenever there isn't a balance established, then we have this decay, radioactive decay that we're talking about. We call anything that is leaving the nucleus because of this instability radiation. There are several types of radiation. You might have heard of these terms: alpha particles, beta particles, and gamma rays. So there's a video that will talk about this a little bit, but there's also, just to help you practice this idea of radioactivity, is a link that you want to click in and check your understanding. You can click on this link right there, or you can go to Join My Quizzes and type in that number code 311478 to check your understanding. Here is a video on the types of radioactivity that will explain the alpha, the beta, and the gamma. Take notes as you're watching this so that you can tell the difference between the different types of radiation. You can check out some of your notes by comparing them with my notes. So radioactivity can produce new isotopes or elements. And we've talked about like that carbon-14. Carbon-14 can actually decay into nitrogen-14. So we have a parent, which is the start element, and what it produces is the daughter element. So unstable isotopes give off radiation. If there are too many neutrons in an atom, it will become unstable and give off particles to become more stable. Well, now that leads us into the 4.07, which is dating. What is radioactive dating? You might have heard that term before. Well, radioactive dating is used to determine how old something is, because we know that radioactive decay occurs at a constant rate over time. So it's the spontaneous decay into a more stable nucleus. And there'll be some examples in here that you can pause and look at, like uranium is a popular one. And again, the parent isotope is the start element, and then the daughter is what it turns into through its radioactive decay. Like we had said earlier, it is at a constant rate. And we call this breakdown from the parent isotope to the daughter isotope half-life. So it takes 1/2. So when 1/2 of an element becomes something else, so if I start with carbon-14 and it slowly breaks down to nitrogen, when it reaches half of the amount it started with, so if it started with 10 grams of carbon-14, when it reaches 5 grams, that's considered 1 half-life. However long it took for that to break down is considered 1 half-life. And then 1/2 of that 5 grams, which would be 2.5 grams, as soon as the carbon-14 sample the sample they have only has 2.5 grams of carbon-14 left in it, then it hits its second half-life. So what they're doing with the half-life is they're measuring a sample and then going through and determining how much carbon-14 is still present, how much nitrogen is there. So as one breaks down towards the other, they're comparing the ratios of what is present. Here's another example of that. You start with a sample and you take the measurements. So that is 100%. The first half-life occurs when half of the original amount of whatever substance, whether it be carbon-14 or uranium, is still present. And you can go through, pause, and read this and look at this chart so that you can understand it. There is another way to draw this. You can also draw it as atoms, each atoms. So you have your initial rock right there, and then how it breaks down over time. They just count the atoms. Here's another chart of that explaining the half-life to help you out. Half-life of an isotope is related to its radiation danger. We know some types of radiation and some types of elements are dangerous to us. The longer the half-life, the more stable an atom is and the less radioactive it is over time. But each of these different isotopes have different half-lives. Well, we use this to calculate age in science. So here is a video to help you on how it's called radiocarbon dating a lot of times because the atom being used is carbon. There's not always carbon being used, and that video will talk about it along with this material. Know that there is always a margin of error. It's not perfect, and we are learning as we go. These are just theories. Everything's a theory. We just modify and add to it. But you can test out this information by going to a PhET simulation and check it out. It gives you different atoms and it will chart how they decay. So you can go through these slides to help you. Here's a couple pictures for when it's on half-life, what it could look like. Then it also has and shows decay rates. It will show you the graphs and you can watch it occur over time. So this is a still shot, but you can see that it will change over time. When I snipped it, it was near the end of its end of the graph right here. And you just use this toggle back and forth to slide how many nuclei you want to have present in your sample. There is also, you can see how they would graph it with an object. They have a tree here that you can plant a tree or place a rock, and then you move this probe over to the specimen and it will chart it for you. It's kind of fun to see, but that's there to help you. So remember, by the time you're done with this material, you want to be able to define what half-life it is, and then to be able to try and calculate a couple of these samples. So if 60 uranium atoms exist at time 0, how many uranium atoms will there be after one half-life? Hopefully you pick C, 30. So 1/2 of 60 is C. Here's another question for you. If 60 uranium atoms exist at time 0, how many uranium atoms will there be after 2 half-lives? So calculate that out. If one half-life is 30, what is 2? And then if a substance is emitting radiation very slowly, what would you say about its half-life? Hopefully, it's a long, stable life. So this information's there to help you to calculate it out and think about how scientists use this as they date things. If you have any questions, please let me know. Have a great day. We'll see you next time.